This is the solution to random MathStat problem number 187. In this problem, we're given a sequence of independent random variables, x1, x2, x3, on up, and we're given that xn has a binomial distribution with parameters n and p. Note that these random variables are not IID because they're not identically distributed. For example, x2 has the binomial distribution with parameters 2 and p, whereas x5 has the binomial distribution with parameters 5 and p. Those are not identical distributions. We are asked in this problem to investigate the convergence in probability of yn, where yn is defined to be xn over n. In other words, we want to know what this converges in probability to. Recall the theorem we had that said that if theta n hat is an unbiased estimator for theta, and if the limit of the variance of theta n hat is 0, then theta n hat converges in probability to theta. Remember, an estimator is just a random variable, and so this theta n hat is going to be replaced in this problem with our y sub n. Note that the expected value of y sub n is the expected value of x sub n over n. We can pull the 1 over n out, and the expected value of this binomial np random variable is n times p, so overall the expected value of yn is p. If we have that the variance of yn goes to 0 as n goes to infinity, we can say that yn converges in probability to p because yn is an unbiased estimator for p. The variance of yn is, of course, the variance of xn divided by n. We can pull constants out of variances, but remember, they come out squared. Looking up the variance for the binomial distribution, it is np times 1 minus p. So simplifying by canceling an n, we get p1 minus p over n, which does go to 0 as n goes to infinity. In summary, we have that yn is an unbiased estimator for p, and the variance for yn goes to 0 as n goes to infinity. Therefore, we have that yn converges in probability to p by that theorem that we had. Again, yn may not look like an estimator, but in this case, it is an estimator for p. So you could rename yn to be pn hat, and now it really matches up with that theorem.